Warning! Tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Well, I got the output tubes all wired up, powered up, biased, all that part of the amp's done. And one of the other things that was kind of tricky was getting the tag strip mounted for the driver tube without it being visible from the top, or as little as possible. I did fail trying to do a blind hole, but I was able to get a pretty invisible screw hole in the top where I've got the ends of the screws flush with the top of the amp, and you really can't see them. I mean, even when I turn it like that, they're right, like there's one right there, there's one over here. You really can't see them, so I'm happy with that. These little screens turned out awesome. I've been struggling a little bit trying to find some 27 tubes that match, because one of the problems is getting the heaters to be drawing the same current. And when I was putting this amp design together, I was trying to figure out how to do the heaters on these 27 tubes because they pull so much current. And a pair of them wired in parallel pull 3.5 amps, and most of the filament transformers are only good for 3 amps. And so that was going to be a problem. And this power transformer has a 4 amp 6.3 volt winding, so that was plenty of current and too much voltage. And so some dropping resistors and then wiring the tubes in series seemed like a good solution, but really been fighting with that. I've got 4 of them so far, and one tube pulls a lot more current than the other. So one will be sitting at 2.3 volts, the other one's sitting at 2.7 or 2.8 volts. And trying to get a pair of them that are evenly matched as far as the current draw to the heater on these dinosaur tubes is proving to be problematic. One of the tubes I got, I don't know what was going on with it. It was glowing super bright, and then you'd like tap on it and it would glow normal again. So obviously some kind of defect with that. Given these are 90-year-old tubes, I'm surprised they work at all. So luckily they're fairly cheap. I don't mind spending 50 or 60 bucks trying to find a pair that are fairly well matched. I do have a pair right now that I think one of them's at 2.45 and one of them's 2.55, so I can live with that. But they're 2 different brands, which I don't like because they look a little different. That'll be good enough for testing. And once I determine that these 27 tubes will work driving these 47s, I can worry about finding a nice matched pair. So we're going to stop fretting on that. Got the 47 tubes both biased up super nice, like I said. And I'm going to first kind of go over my thought process on getting the amp to this point electrically. And I know a couple of people have said, show us more of the wiring. Well, guys, I'm fixing to show you how I determined the values for all the components to power up these output tubes and get them biased right. And so hopefully y'all can learn something from this and get a better idea of how the schematic works. Next, we need to power up and bias the input tubes. And we got the heaters working, but we don't have any B+ or cathode resistors or anything like that hooked up to it. But I do have a tag strip now, so that's a long way towards that. Then the last thing we're going to have to do is mount the volume control over here and then put the RCA jacks. Since I'm going with cathode bias, I originally was going to put a milliamp meter up here, but there's not a whole lot of point in it being as a cathode biased amp. And if it was fixed bias where it was, you're having to adjust the bias voltage, that does make sense. But since we didn't go that route, I may save that meter for another project. I did pick up one of these really cool little old school fender type indicator lights, the little jeweled ones. So I may put one of those right here on the top so it's not blinding at you, but you can still see when it's on and when it's off because the tubes don't glow that bright. So you could accidentally leave this amp on, which, given the age of these tubes, probably wouldn't be a good idea. It's like, but that's one little option for a little dress-up thing. But let's get the thing working first, and then we'll worry about making it look pretty. So anyway, let's jump into looking over the schematic, and then after that, we're going to flip the amp on its side. We're going to power it up with the variac and the isolation transformer and get this thing powered up so we can measure the voltages or show y'all what the voltage measurement's like. And then we'll be getting closer to getting this thing into being a real amplifier. So let's go over the schematic and try to understand how this amp operates. Okay, so let's show you where we're at right now and how we basically designed this output stage of this amplifier. So first we start with the tube data sheet, and this Cunningham radio tubes data sheet had a lot of good information, so this is what we worked from. First we have the filament voltage, which is 2.5 volts. And here's our filament current, which is 1.75. So we want to make sure that whatever we're using to drive these filaments can handle this much current, which the two tubes together is 3.5 amps. Or if they're being driven individually like we did on this amp, they need to be able to handle at least 1.75 amps. The plate voltage, 250 max. Screen voltage, 250 max. One thing that I've learned about pentodes is they like having the screen voltage slightly less than the plate voltage. And so that's what we're going to be shooting for. The grid voltage should be negative 16.5 volts or something close to that. The plate current, which is the max, is 31 milliamps, and then the screen current is 6 milliamps. Another thing to pay attention to here is the load resistance, and it's telling us that 7K is the load that this tube wants to drive, which means we want a 7K output transformer. Those are the main things that we want to be paying attention to. So if we read through this text, it talks about how to place the tubes and that sort of thing, and vertical and horizontal and all that kind of stuff. And then talks about it can be a single-ended or push-pull. Says that more than one audio stage preceding the 47 tube is undesirable. So really we want to try to figure out a way to have a single stage driving this. I know at one point I had talked about using possibly 2 stages, but if I'm reading this and just thinking about it more, we're going to use this 27 tube, and then if that doesn't work, we're going to go to the 56 tube. So here we're talking about if it's self-biased, the self-biased resistor should be approximately 450 ohms. So we'll take that into consideration. Talks about the bypass cap should be a minimum 4 to 20 UF. Well, actually, we're going to be trying to get this tube to amplify frequencies a lot lower than what they intended. And so we're going to be using a 220 UF to bypass this resistor. And then it talks into push-pull, that kind of stuff. Talks about the input coupling. The grid resistance should not exceed 0.5 mega ohms or 500K. So we want a resistor that's somewhere around 500K. I wouldn't be scared of using a 510K. That's really close to this. Or a 470K. Either one would be fine. We want to keep that as high as possible because it makes it easier to drive by the input tube. And then it talks about blue glow, frequently appear. Unfortunately, I haven't seen that yet. I was hoping I would, but who knows? Maybe when it gets some time on it, it will. But here's the chart that's very useful, is the plate characteristics. And they've drawn the 7K load line for us. Goes at an angle across here. You can see how linear this tube is. The gaps between, especially when you get around the bias point, it's very linear in this range right here, which is what we want to see in a tube used for audio. We also see that biasing it somewhere along this 16 volt, 15 to 16 volt range is ideal, and that's what we're shooting for, is to bias the amp right here so it's in the middle of this load line, so we got plenty of room to swing on each side of it. So if we get the bias around 15 volts, that means we need about 28 to 30 volts peak to peak to fully drive this amplifier, which shouldn't be too hard to come up with. So next we start drawing up what this output stage is going to look like. And this is simplified down to just the output stage. So we have our 7K UL output transformer. So to get this 250 volts that we want to see on the plate, we want a B plus that's at least 255 volts, something like that, but probably not more than 265. So there's a range there that we're shooting for on our B plus. So even if we have 265 volts here, we have 15 volts sitting here. So you take the 265 minus the 15 and you're at 250 volts and you're right at the maximum. So ideally we would see 260 volts or something like here to give us, a few volts of headroom. And that's what we're shooting for. But anything from, 250 to 265 would work fine. The other thing is we want to see 5 milliamps across this resistor to the screen. And we want to see 5 to 10 volts less on this screen than we see on the plate. And I'll explain that in a minute. This is showing plate voltage here, screen voltage here on this pin. Because this is a direct heated pentode, these two arrows here go to the heaters, or the heater transformers that are supplying the 2.5 volts for the filament. And then we're pulling the cathode off the middle of those, off this hum pot or potentiometer here across the heater. And then this comes down to our 500 ohm resistor. This is our bypass cap that bypasses the resistor, and that goes to ground. Over here we have the grid leak resistor, which is 470K, could be a 510K, somewhere around in there, around 500K, that's referencing the grid to ground. And then this point right here is where we're going to be injecting the signal from the input tube. But I drew it up as just the output stage because that's what we have wired up right now. So let's look real quick at the pentode that's in this amplifier. And this is our common picture of a pentode. We have our plate here. We have our screen right here. We have our grid here. This is called a suppressor grid. And then this would be the cathode. And then here would be the heaters. And this is what an EL34 looks like. The suppressor grid is here so that as the electrons flow up through the tube, because they go in from negative to positive, when they try to bounce off this plate, this suppressor grid repels the electrons back to the plate, which makes the tube more efficient. The screen is here with some voltage on it to help accelerate the electrons from the cathode to the plate. But you want it to be a slightly lower voltage so that once the electrons get to the screen, there's more potential to attract them here at the plate than there is at the screen, so they go on by the screen and go to the plate. The grid, as it goes up and down in negative voltage, either repels the electrons back to the cathode or it lets them flow through to the plate, and that's what controls the tube. And then the cathode here is the negative where the electrons are emitted from, and the heater heats up the cathode. Well, because we only have 5 pins, and if you look at this tube, it's got 1, 2, 3, 4, 5, 6, 7. And we only have 5 pins to work with. And so this is what this tube looks like. We have a plate. The suppressor grid is tied to the cathode internally. So we have our screen, our grid, and then we have a directly heated cathode, which the heater is the cathode in this tube. So let's take a look at the power supply. And this is the power supply that we've come up with. We're using this Hammond 370EX transformer, which is 144 milliamps, 275, 0, 275. And then we have 3 amps at 5 volts and 6.3 volts at 4 amps. And we're going to be using this 6.3 volt with a couple of 0.4 ohm resistors to drop the voltage down to these series connected heaters on the 27 tubes. We have 2 separate of these Hammond 166L2s that are 2.5 volt, 2.5 amp. We have 1 per channel, and these go to the hum pot or the potentiometer that's across the heater on the power tubes to heat up the heaters in those 2 tubes. So here's our type 80 rectifier tube. We have the high voltage going to the plates, the 5 volt heater. This is a directly heated rectifier tube, and the high voltage is pulled off of this leg of the heater, pin 4. First we have our first filtering cap, which is a small 10 UF. Normally we use a little bit higher one, a 22 or 33 UF, but since this is such an old tube, I didn't want to put too much capacitive load on it, so we're just going to use a 10 UF there. We have this top mounted 5 Henry 65 ohm resistance across it, 200 milliamp choke as our first filtering choke. Then we have a 47 UF cap after it. Now here we had 2 different chokes that we could potentially use to adjust our B plus voltage. And both of these are 100 milliamp chokes, which is plenty for this amp. One of them has 170 ohms and one of them has 80 ohms. And the difference between a 2 and a 3 Henry isn't really that critical or really even that important. What we're looking at is this ohms drop across them. And after this we have 100 UF, and then there's our B+. In this case, after some testing, we ended up going with this 154M that had the higher resistance so that we could get the B+ down to what we wanted, which we ended up with 265 volts on the output of this power supply into our circuit, and that's right where we wanted to see it. So, how did I design the power supply? We used this software here, PSUD2. We've got the 80 tube here. We have our 275 volts on the transformer. We plugged in our capacitor, our choke, capacitor. Here's our potential load, 65 milliamps. Then have another dropping resistor, which is maybe 2K, we're guessing. And we just play around with some of these values till we get out of this what we're looking for. And then here's the decoupling cap, and then these are the driver tubes. But right now we're going to focus on the output stage right now. And as you can see with this voltage at I1, which is right here, our load, it's estimating that we're going to get 256 volts. So this is what we built the power supply like, and that's real close to the voltage that we got out on our load. So anyway, I hope that helps you understand the design process on how we got to this point in designing this circuit. And now we're going to jump back to the amplifier and do the quick voltage check on it. Okay, since the last episode, we've wired up the B plus to get it completely done. Right here is our bleeder resistor that goes across this second capacitor. Here's the choke that got mounted over here in this corner. We ended up using the smaller 154M 2 Henry 100 milliamp choke that had a little more resistance. This one has 180 ohms and the bigger one had 80 ohms, and we needed the extra resistance to drop the voltage. So it goes from this pin to the choke, then back over to this terminal, which is our B plus out, which is the positive of this second 100 UF cap, and then it runs across on this white wire over to this point right here. And this tag strip makes a real convenient place for us to check all our voltages, because this will be the B plus going to the output transformer, as this will be. Those will be the same voltage. And then over here, we can check the plate. We could check it either over here or over here on the tube. We'll probably just go ahead and check it at the tube. So this plate wire got run from the output transformer tag strip over to the tube. Then here's our 2K resistor for the screen, and it goes from here over to the screen, and then on this side over here it goes from here to the screen, from here to the plate. So we can check our screen voltage here, check our plate voltage here. We can check the B plus going into the whole output stage, and then on each of these pins we can check the bias or the voltage drop across the cathode resistor. And we've already checked the voltages on all the heaters and they're within spec, so I'm just going to show you checking the high voltage going to the output tube in this segment of the video. Okay, and so we have a great place right here to get our ground. So let's start looking at what the voltages are on these tubes. So the first thing we want to check is the B plus coming over to this tag strip. And again, use one hand and keep the other hand behind your back to make sure that there's no electrical path across your chest through your heart in case you do touch something wrong in here. So here we got 265 volts going to the output transformers, and obviously this one over here is going to have the same voltage because it's just got a jumper going across here. And that's exactly the voltage that we want to see. So I'm super happy that we were able to get that voltage. I mean, that's exactly what we want. So I'm going to go over here and check the plate on this tube. And there's 257. And the plate on this tube is 258. So again, we were shooting for probably 260. So to only be 2 volts off is just almost nothing. That's within 1% of our target voltage. So the next thing we want to check is we want to check this screen voltage. We want to see less than that, 5 to 10 volts. And there's 251. And then over on this side we've got, again, right at 251, 250.7. So these are pretty close matched tubes so far. The other thing we want to measure is the voltage drop across this resistor. So we have, again, 251.3, and then up here 261.21. Basically we have 10 volts dropping across this 2K resistor. And if we do the math, that ends up with 5 milliamps going across this resistor, which is how much current the screen is drawing, and the max is 6. So we're right there where we should be. The last thing we want to check is the voltage on the cathode of the tubes, which will be right here. And we got 14 volts on that tube. And 14.8 on that tube. And given that we're dropping this across a 500 ohm resistor, that's, I have to do that accurate math, but that's 28 to 30 milliamps across the tube, which is, again, right what we want to see, under spec, not stressing these old 90-year-old tubes too much, but pushing them pretty close to their limit, especially on the voltage. So we've got 256 here, and then we've got 15 volts here. We're a little over 240 volts across the tube, which is 10 volts under the max, which should be safe enough for these old tubes to keep them from melting on us. And the same thing over here. We got 257. And then 14. So just a little over 240 volts across that tube as well. So we've now got these tubes biased, running, conducting current. They're ready for an input signal. Well, as you can see, the simulator was really close to what we ended up actually getting out of this transformer and power supply. So that's a great tool for kind of mocking up power supplies for tube amps and figuring out what kind of voltages you're going to get out of different combinations, and then what kind of ripple voltage you're going to see out of them as well, and how much filtering you need. So I think that all turned out excellent. I'm really excited to get this part of it done. To me, this is something that sometimes you struggle with, is to get the B plus right where it needs to be. And given the vintage of these tubes, I want to run them close to what they're saying the maximum is, but I probably don't want to go too much past that, like I might with a more modern tube. The other thing, got to get these biased up now and see how these 27s bias, and then hopefully we can get enough voltage swing out of them to make this amp reach full power without having to go to some other kind of tube. Don't think it's going to be real hard coming up with 30 volts peak to peak out of a modern source, because they're pretty hot. Back in the day, they were trying to drive these things straight off of like a phono cartridge or a really weak radio signal, and so they really did struggle to get full power out of one stage. But like the data sheet said, we really should try to make it a one-stage amp if we can, or two-stage, one driver and one output. So anyway, hope y'all are enjoying this series. I'm having fun building this amp. This has been kind of a slow process for me. Unfortunately, I've had a lot of life stuff get in my way. Family problems this last week delayed things again. But I am moving forward with this thing, and hopefully within the next week or two, we're going to have this thing on the Analog Discovery 2 and on the oscilloscope, and be looking at what kind of performance that we get out of this thing from these 90-year-old tubes. So if you're enjoying this content, please subscribe to the channel. That helps get it out there in front of other people that might find this stuff interesting. Like the video, and we'll see you soon. Have a great day.